Hello, dear physicists. Permit me to spin you a tale of distance and displacement. They're both useful. One of them's a little more useful than the other. We should talk about the differences and how to figure them out, okay? So, very quickly, very briefly, distance and displacement. Let's start with a rough idea of what we mean. When we're talking about distance, we mean how much ground do you cover? Turns out distance is surprisingly difficult to define really neatly. Displacement, on the other hand, is very easy to define. It is where do you end up compared to where you started. Okay? I think examples should make this a lot clearer. Let's suppose we have a little kid. A little kid. She is very, very little, right? Because I noticed that's a centimeter scale there. So this is an extremely little kid, right? Little kid, and, she lives in this house right here at the 4 mark. And, there's a number of enjoyable things in the neighborhood. Like, there's ice cream to go get at the 10 mark. There's a slide to play on at the 0 mark. And heaven only knows what in between. So let's just do some really basic things. We're going to start just talking about displacement. So displacement, recall, it's where you end up compared to where you started, but it's also direction. Direction matters with displacement. So, and in what direction? So we're going to name our directions here. We're going to name our directions. Let's say this is the positive direction over here, because that's where the high numbers are, and this is going to be the negative direction over here, because that's where the low numbers are. If our kid goes from home to the ice cream, she starts at 4, she ends at 10. How far away did she end up? 6 centimeters away. In what direction? The positive direction. The displacement is positive 6 centimeters. Okay, let's try another one. Let's suppose that she starts at her house and she goes to the playground. How far away did she end up from where she started? 4 centimeters. In what direction? The negative direction. The displacement here is negative 4 centimeters. Okay. Now, what happens if she does this? What happens if she leaves her house, she goes to the playground, she plays there for a while, and then she's like, oh, I've got to have ice cream, and she goes to the ice cream joint. Now, all that displacement cares about is where she ends up compared to where she started. Let's mark these things. Where did she end up? Here. Where did she start? Here. So, where did she end up? She ended up 6 meters away in the positive direction. The displacement is positive 6 centimeters. I said meters before, didn't I? Doesn't matter that she went to the playground. The displacement is just 6 centimeters. What happens if she does... What happens if she does this? What happens if she goes from her house... Oh, for heaven's sake. What happens if she goes from her house to the ice cream place and back to her house? Where did she start? At her house. Where did she end up? At her house. How far away is that? 0 centimeters. The displacement here is 0 centimeters. Displacement only cares about where you start, where you end, and what direction you end up in. Do you end up in the positive direction or in the negative direction? One other thing we're thinking about with displacement for later is that another way of thinking about displacement is thinking about displacement as delta position, where delta, as you probably know, is our science way of saying change in. Displacement is change in position, and the way we calculate that is we take the final position and we subtract the initial position. That may seem overly complicated in a situation like this, where you can just look at it and go like, I can see she went 6 centimeters, but humor me. She starts at 4, she goes to 10, our ending place is 10, our starting place is 4, we take the final position, 10, we subtract the initial position, 4, and we end up with a displacement of positive 6 centimeters. So that's the other way of thinking about displacement. Change in position. Final position minus initial position. Sometimes you'll see people, because this number line here in math is often called x, so the initial position is x with a little I to mean initial, the starting position, and the final position is x with a little f to mean final position. Sometimes this gets written, change in position, as delta x equals x final minus x initial. And this is different from the x you use in math, where you just use x for anything that's unknown. Here, x is like where you are. That's what we mean by where you are. And we're just using it because that horizontal line often gets called x. It's just common in physics. Okay? That's displacement. Where do you end up compared to where you started? Now let's talk about distance. So I said that distance is a little harder to define, and distance is the amount of ground you cover. So we go from here to here. The distance equals 6. And by the way, I should have said this. In physics, when we use a lowercase d, we mean displacement. And in fact, there isn't even really a proper symbol for distance in physics. So we sometimes say things like distance, or if we're being really formal, well, anyway, we're just going to say distance. We'll just say distance. Doom the loom. Okay, so if we go from the 4 to the 10, how much distance do we cover? Oh, we covered 6 centimeters. That's this also a displacement, right? We have a displacement of 6 centimeters and a distance of 6 centimeters. If we go from here to here, if we go from home to the playground, we said that was a displacement of negative 4 centimeters. The distance is just 4 centimeters. Why? Because nobody talks about negative distance. Nobody says, oh, you know, how far is my walk to school? Yeah, I've got to walk, you know, negative half a mile. We don't do that. When we say distance, we just mean how far, how much ground do you cover? So the distance here is equal to 4 centimeters. Now, I also said distance is harder to define. And if you know some math, you might be like, well, isn't distance just the absolute value of displacement, right? If you know about absolute values, no big deal if you don't. And the answer is no, because this is where life gets a little trickier. So what if So let's go back to the situation of going from home to the playground, turning around, and going to the ice cream. What's the distance? It's the ground you cover. So let's just take a look at it. First, our kid has to go from here to here and cover 4 centimeters. Then our kid has to go from here to here and cover 10 centimeters. What's the distance? 14 centimeters. So distance you kind of have to figure out by looking at it. You have to say, oh, where did I have to go? And even if I had to double back, it's like if you go from home to school and back to home again, your displacement may be 0, but you still had to cover all of that distance. If that was all walking, you still had to do walking. You can't be like, oh yeah, I only had to walk a displacement of 0 meters. It's like, how does that explain how tired you are, right? Okay, that's distance. Distance, how much ground you cover. Displacement, how far away you end up, or delta x. But we don't usually see these things on number lines. So let's just talk about this from a graph type of perspective. So here's the situation of going from home to the ice cream store. The way we see that on a graph is like, oh, horizontal axis is time, vertical axis is position, and we say, oh, where was she at the beginning of the story? Well, she was at her home. That's at 4. So the 4 mark is right here. So at the beginning of the story, she's at the 4 mark. And then let's say that our story starts at time 0 and ends at time 6. So that means that at time 6, she has to be at the 10 mark. So I'm going to find the 10. I'm going to go over here. This is where she is at the 10 mark. And so when she goes on this trip for 6 seconds, she's going from here to here. So this might be our graph of her travel. Again, how do we find the displacement? We would go, okay, where does she end? 10. Where does she start? 4. This is where I find it easier to do final minus initial. I go like, oh, 10 minus 4 is equal to 6 centimeters. Awesome. Boom, done. What about if it's negative? What about if she goes from home to the playground in 6 centimeters? Okay, she starts at the 4 at the beginning of the story, and 6 centimeters later, she's at the playground. She starts here, she ends up here. Not the straightest line in the world, but you get the picture. So that's that trip appearing on the graph. Just a little note, maybe this was obvious to you, but if you missed it, if you're looking, wait, what's going on with this graph? I just want to point out, one of the things that's tricky here is that we take these position numbers, and when we make the graph, that's on the vertical. And this drives some people nuts, because all of a sudden what you have to do is you have to be like, okay, well, this is X. I said this was X. So now the vertical axis is X. And they're like, wait. In math class, X is on the bottom and Y is on the top. And if that drives you nuts to have X up and down, that's okay. Don't write X, write position. But you know, math, it's always the same way. In physics, we go like, oh, what are we graphing? Well, we're graphing time against position. We're calling position X, and that's what we got. Displacement, initial, final. We take the final, 0. We subtract the initial, 4. We get a displacement of negative 4 centimeters. That's the displacement. What's the distance? The distance is just how far you had to go from 4 to 0. So the distance is just equal to 4 centimeters. Now let's see what happens when she doubles back. Boom. Okay. Now she goes from home to the playground, turns around, and goes to the ice cream store. Okay, so let's put the beginning and the end here. She goes from home. She starts at the beginning of our story. Here's our time axis. The beginning of the story is 0. At the beginning of the story, she is at the 4 mark. We know at the end of the story, here, she's going to be at the 10 mark. We also know that in between, she's going to go to the 0 mark. So here's the 0 mark. So somewhere in between, she has to hit this place. Now, you know, in this story, we don't know specifically when, so I'm just going to make this up. I'm going to be like, oh, look, she goes to the playground. She's going back. And then she goes to the ice cream store. What's the displacement? Final position, 10, minus the initial position, 4. 10 minus 4, the displacement is positive 6. What's the distance? Well, how far did she have to go during this part of the story? Well, she had to go from 4 to 0. So this is a trip of 4. And then from here to here, how far did she have to go? And notice I'm going up and down because we're reading off on the vertical axis. This is 10 centimeters. So the distance is all of that added up, forgetting whether it's positive or negative. So we get a distance of 14 centimeters. Last thing I want to point out, I should get a bigger eraser. Is that in this particular story, I start at 4, I end at 10, and I just have to get to 0 somewhere down here. So I drew that earlier as straight lines, but this could be something like this. Right? We could make all kinds of shapes in between, and the shape would tell us about how fast she's going, but that's for another day. Let's do this once when we just have a graph. If I have a graph that goes from here to here, how do I find the displacement? I take the initial position, that's 6, I subtract it from the final position. X final minus X initial. The final is 1, the initial is 6. I go 1 minus 6 is equal to negative 5 centimeters. If I go from here to here, that's a displacement of negative 5, and it's a distance of 5. I'm going to go straight to a harder one. What if I start here and I go from here to here? Okay, well, the displacement, again, is the final position minus the initial position. The final position was 1. The initial position is 4. So I'm going to go 1 minus 4. The displacement is negative 3 centimeters. Awesome. The distance, I have to be more careful about. The distance, I'm going to go from my 4 to my 9. Ooh. So that first half of the trip, 4 to 9, I have to go 5 centimeters. And then the next part, I go from 9 down to 1. 9 to 1 is a distance of 8 centimeters. So, oh, what do I have? I've got 5 and I've got 8. The distance, 13 centimeters. So there you go. Those are some examples of distance and displacement, reading both on a number line and on a graph. Hope that was helpful.